In this video, we're going to take a look at how to measure execution time of a process. So to start off, we're gonna have to create first a set process. So I'm gonna have here a simple for loop, right? I'm gonna create here, let's say, I don't know, say int x equals 15 for, let's create a long I equals 0, and I'm gonna have it go up until, oh, I don't know, let's say 10 million. All right, and then I'm gonna say a++, and x times equals, I don't know, 2, let's say. I don't care about it overflowing. So if it overflows, I don't really care. I just want it to do something for a really long time. And this seems sensible. So if I try to run this, we should see that, well, it doesn't take too long. So let's add another 0, I guess, and make it a bit longer. And that's about good enough. And now let's say we want to know how much it actually took to execute this part of the code. In general, there are at the very least two very distinctive ways of measuring execution time of any process, but they both rely on a very simple concept. You, at the beginning of the process, before it starts executing, you simply get a beginning timestamp, so beginning timestamp. Okay, so you get here, for example, the seconds at the clock, and after the process that we want to measure finishes its execution, we're just going to get another ending timestamp. And after getting both of those timestamps, we simply display the difference between the two timestamps. That's the basic gist of basically any code that's trying to measure the execution time of the process, okay? And this difference, you can think of it as subtracting the number of seconds at the clock, let's say we include the minutes and whatever else, okay? Now, regarding the actual functions that we're gonna use, we're gonna start off with the first way of doing it, and it is to actually get the wall clock, literally the internal clock of the computer. We get it here in the beginning, we wait for the process to finish, we get the clock at the computer again, and then we subtract those two timestamps. And that's the first way of doing it. And we're going to do it through a function called timespec_get, and that can be found in the time.h header. So I'm going to include that as well. And here you can see it takes a reference to some variable that we have to define and initialize. So we're going to say here struct timespec, let's say begin, I'm going to call it begin, and I'm going to pass in a reference. And here you can just pass in the time_UTC constant. That's basically all there is to getting the beginning timestamp, and then to getting the end timestamp, you just copy and paste this stuff here, and I'm going to just change it to be end. All right. So now that we have the timestamps, we can simply display a difference between these two. Now, how do you actually do that? Because you might have noticed that this timespec variable type is not just an integer, it has two variables. And if you have the documentation at hand, you'll see that it has two members. It has the number of seconds that have elapsed, and then it stores also the number of nanoseconds. So we have both of them stored separately, and that means that the clock, or the time that we are measuring in, is at most correct at the level of nanoseconds, okay? And that we have them separately, we kind of have to get a, what's a number of seconds in a floating point variable. So how do we do that? Well, a very simple way of doing it is to just define here a variable of type double, let's say. If you want more accuracy, you can change this to something else. I'm gonna just use a double here and say time spent, let's say. And first I'm going to subtract the seconds. I'm gonna say, let's say here, end.tv_seconds minus begin.tv_seconds. So that's fine and dandy. Now we have the number of seconds, but I'm going to also add the difference of the nanoseconds. So just end.tv_nsec minus begin .tv_nsec. And since these are nanoseconds, and what we want to store in here is the number of seconds with decimal points in it, what we're going to do is divide this number by how many nanoseconds are in a second. Well, we know that 1,000 milliseconds represent a second, 1,000,000 microseconds represent a second, and 1,000,000,000 nanoseconds actually represent a second. So we need to actually divide this by 1,000,000,000. So 1 followed by 9 zeros. 1, 2, 3, 1, 2, 3, 1, 2, 3. I'm going to say .0 here so that it converts everything to double. Okay, it treats it as a double. Great. Now we have the end result, and we can simply display it on the screen. Let's say printf time it took to execute. Let's say percent. I'm going to say %lf because it's a double. Time_spent. All right, perfect. Now, if we try to launch this, we should get a result. And we say time it took to execute, that is 0.07 seconds. Okay, let's say that we had a couple more zeros here at this multiplication process, and we should see that it takes much longer. And well, after we finish its execution, we can see that it took at least my computer 5 point something seconds to execute, and that seems about right. Okay, that's about how much it took for me to wait for the process to finish. Well, this method of measuring time is fine unless you have limited CPU resources, because if at some point the operating system decides to stop this process in order to let other processes run in the background, well, this measurement is going to also add those seconds, because we're simply looking at the wall time, and it's going to be like, okay, well, this is at 00 and this is at I don't know, 10 seconds, even though like 5 seconds we've spent just waiting, doing nothing because other processes got in the way. So this is not quite perfect, especially if you have to take into account time changes. So if for whatever reason you have to synchronize your time with the network and things go wrong, this type of measurement is not great. And actually we can simulate this. So let's say I change this to, let's say 10 times faster to be executing. So if I launch this, I should get about like half a second. Yeah, okay, 0.78. So let's say if we add here a sleep of 2, of course before taking the end timestamp, and I include here unistd.h for that sleep call .h, there we go. If I try to launch this, you will notice that it takes 2.68 seconds, even though for 2 seconds our process didn't do anything at all. Now the second way of measuring process execution time is using a sort of timer that takes a look at the CPU time that has been elapsed since the start of that timer until the end. And that is where the clock_getTime function comes in. So here we can call clock_getTime, and here we need to specify what time we want. Here in the time spec get, we didn't have to specify anything because this is part of the standard, okay? But clock_getTime is not actually part of the C standard, it's just part of the POSIX standards. You can use it on Linux and Mac, but on Windows it's a bit different. So this guy takes in a constant, and I'm gonna use here clock_process_CPU time_ID. So this is what we want, the CPU time itself. And as you might notice, it also takes in a reference to this time spec. So I'm gonna actually create a new one. I'm gonna add it, let's say here, call it begin2, and we're gonna pass in a reference to begin2 so that we actually get the time of it. And similarly, after the end of this one, I know it's not recommended to use both of the timing functions in the same process, but right now it's just for demonstration purposes. You'll see later on. But right now, I'm going to instantiate this, call it end2 that way, and let's do the same basically, since we have the same exact type here, we can just simply copy and paste this here and call it time spent 2, and use, well, I'm going to use 2 here everywhere and here as well. Perfect. So it's exactly the same idea as before. And we can say here time it took to execute. I'm going to call it CPU time. Let's say that. I'm going to say wall time. I'm going to type in here time spent 2. Now if we try to launch this, let's see what happens. You will notice that we actually get two different results. We get wall time, and that is 2.6 seconds. That's exactly how much on the wall, the clock on the wall said that it elapsed, and definitely we have waited more than 2 seconds. But the actual CPU time was only 0.68 seconds. And of course, if we, for example, remove the for loop altogether, we're gonna probably see a very, very, very minuscule amount of time that has been used by the CPU, or that the process used the CPU. Great. So now we have these two ways of measuring time. You can start using it if you're on Linux. Both of them are available. No problem. But if you're on Windows, this is a bit more tricky. Now, interestingly enough, you might say that, yeah, sure, I always want to use the CPU time counter, of course, right? But there might be some cases where you actually want to use the wall counter. Let's say that, oh, I don't know, you have some sort of, let's say printf here that says, I don't know, test \n, and let's call it only a couple times here. Let's remove the sleep call here. If we try to launch this, you will notice something very interesting. As you can see, the wall time is much larger than the CPU time. Actually, if I add another 0, you might actually notice that it does take about 4 seconds or so to execute the whole thing, even though the CPU timer actually tells us that no, it actually waited 1.4 seconds. That's because printf usually has to wait for the standard output buffer so that it can actually write things to it. We have used this actual terminal to write things to it, and the process, our process that tried to print something on it had to wait for the terminal to display all this text. So in this case, I might want to see the wall time because I might be doing something wrong. Let's say that I'm writing, maybe not on the terminal, but maybe I'm writing on a file. And that writing operation actually doesn't require CPU time 100% of the time. Okay, so some parts of the operation might be because, well, we're waiting for some process to finish reading this file, or we're waiting for some handle to be passed to us by the operating system. And that type of time is not accounted by this CPU time counter, but it is accounted by the wall time counter. So it is all circumstantial. You would want to use one or the other based on what exactly you want to measure. Okay, so if you want to just count the actual CPU time that your process has used for the execution, regardless of how much it had to wait for the terminal, for the files to write, or how much it had to sleep, for whatever reason, if you just want to, know the actual calculations, the time it took to do the calculations inside of the process itself, use the CPU time counter. Otherwise, you can use just a wall time counter, and that's perfectly fine. That's basically it. If you're using Linux or Mac, you can already start using these measurements perfectly fine. You can go now. But if you want to learn more details about these and how to actually use it on Windows especially, stick around. First things first, I want to show a few more details regarding the implementation of this timespec get. So timespec get, I said that it's in the standard itself, right? That's perfect. You can use it both on Windows and on Linux without any issues. It's basically the same thing. Interestingly enough, timespec get actually uses this clock_get time function. So instead of using timespec get, what you can do is simply say clock_get time and simply pass in here clock_real time. Okay, and then it doesn't need a time UTC thing, and this is basically the same as we had previously. It's just that it's using the same function. So if you want, you can do so without any issues. Now, copying over the code to Visual Studio here using the MSVC compiler doesn't actually, well, let us compile it, of course, because it doesn't have this clock_getTime function. So we're going to actually remove this. So this goes away, and this goes away, and of course this time spent variable also goes away. All right, we're going to have to come back to this. And I'm going to remove uni_std.h. We don't need that anymore. How do we actually get the CPU time on Windows? Because for the wall time, for the measurement with the wall time, that works. We have timespec_get, that works perfectly fine. We can use that. Now, getting the CPU time that has been elapsed on Windows is a bit more involved. To start off, we're going to include windows.h, like so. All right, and here we're going to have to use a function called get process times, and it's defined here. As you can see, it's a bit of a long line of parameters that we have to pass, but it's not that complex, trust me. To start off, we're going to actually define those variables because we have to pass references to those. So we're going to have here a struct, and those parameters are of type file time, and the first one that we're going to have here is begin_to. This is our beginning time, but we also need a couple more things here. Namely, we need creation time, so we need to take in the creation time, we need to take in the kernel time, and we also need to take in the exit time. This exit time. Okay, so these are the 4 variables that we have to pass in to get process time. All right, as the first parameter, you might notice it's actually the process handle, and that's simply we can get it from the get current process function, and then the 4 variables we just simply pass them as references. We're going to say here creation time, right? Then we have the exit time. We don't care about that because that's basically the time the timestamp at which the process exited. We don't care about that. And of course the kernel time here, and the last time is the user time, which is our begin_to that we are gonna use in our calculations. Perfect. And now we just have to do basically the same thing at the end, right? So getting the end timestamp. Here I'm gonna actually define file time end_to, and because I don't care about these other variables, I'm just gonna reuse them, of course, and just gonna pass in end_to here. Perfect. Now we need to calculate this time spent here, and here's where it gets a bit more involved. Here we have to define a couple variables, and one of them is going to be of type ularg_integer. And I'm going to call it, let's say, ul begin_to in this case. And this is going to be a bit interesting. We're going to have to basically set the low part of it to be the begin_to.dw load datetime. Okay, so we're going to basically convert this datetime struct to a ularg integer, which is literally just a complex union of dwords, and dwords are just literally unsigned. Well, in this case, are unsigned long. So it's basically a fancy integer type. So okay, we're gonna use this ul begin_to.highpart equals begin_to.dw highpart. Yeah, there we go. And basically we have to do the same exact thing for ul end_to. And lastly, we can actually calculate this time spent. So we can say double time spent 2, I'm gonna call it, and let's say here it's going to be ul end_to.quadpart. This is basically just a long. So whatever I say here, quadpart is literally just the, as you can see, unsigned long, and if I go over the definition, it's just an int64, which is unsigned, so it's just a 64-bit unsigned integer. So we can just do that, and then we're gonna use the same thing for the beginning part, and of course we're gonna have to divide this difference so we get the number of seconds. Now, important thing to note here is inside these variables we have the measurement is not in nanoseconds but hundreds of nanoseconds. Okay, that means that if we divide by 10 we're gonna get milliseconds. Okay, so that's great. But then if we divide by a million again, we're gonna get the number of seconds, so we have to divide by 10 million in this case. So it's a bit more different than what we did before, but 123, that should be 10 million, and I'm gonna put a dot zero again to consider it as double, and then we should be good to go. Now if I change this, actually I'm gonna leave it this way right now. This is 100 million iterations, so we should see a little bit of CPU time usage. If I launch this, if I get the command line command prompt here, you can notice that indeed we have some CPU time usage, and the wall time is basically the same because we're just doing calculations. So right now they are not different. Let's say we change this to, oh, I don't know, let's do 1,000 iterations, and this time printf this string here. If I try to launch this, it's going to take a bit, but there we can notice that the CPU time is basically 0 because all we did was just print, and the multiplication that we did was only 1,000 times, so barely did anything, but the wall time was indeed a bit longer than that. And of course, if we add another 0, it's going to take a bit longer. If we add a sleep, I'm going to have to add the sleep from Windows. I'm going to have to say sleep with a capital S here and pass in the milliseconds, but that's that. And let's say I'm gonna do, whoops, I'm gonna do calculations again. Say, I don't know, that should be 100 million. And if I try to launch this, we should see, if I bring the command prompt closer, as you can see, there is a 2-second delay between the CPU time and the wall time, and indeed the CPU time actually does give me a result. That's about it regarding the measurement of execution time of processes. You can take a look into more details. I'm going to leave down in the description a couple more documentations regarding the different details on each platform or the different clock types that you can use using that clock_get_time function. But that's, I think you can now take whatever I taught here and actually use it in your program. Maybe in a later video I'm gonna show you how to make a simple macro so that you can easily time anything inside your code if you so desire. But that's it for now. I hope you got something out of this video. If you do have any questions, please leave them down in the comments below or on our Discord server. The code will be available on our website, again down in the description below. Take care.